Electrical and Magnetic Use by Ryan Thomas, March 15th, 2018. Main topics: electricity and magnetism. Electricity is a natural and generated phenomenon. It involves charged particles of either negative or positive, also known as electrons or protons. Negative charge atoms, called electrons, move towards positive charge atoms called protons, creating current flow. Movement of current with turns along the current path can induce voltage near a conductor. This can be seen as an example in a transformer, either stepping up the power or stepping down the power in relation to the number of turns on the secondary coil. Magnetism is a natural and generated phenomena, as in electricity. It has two opposite charged sides called poles. Those poles are labeled north and south, or positive or negative. Opposite sides attract and repel vice versa. Electrical current can be manipulated, which will change the magnetic field. Moving a magnet quickly near a magnetic material can cause electrical current flow. Notice the relation. The relationship between electricity and magnetism is called electromagnetism. The spinning of electrons in a nucleus of an atom causes magnetic field. This means if we have electrons spinning in a direction and we have an equal amount of electrons spinning in the opposite direction, whether it be clockwise or counterclockwise, that will equate to a zero magnetic field. So, taking that thought, if we had more electrons moving clockwise than we did counterclockwise, there would be a magnetic field in a direction. It would have a vector. It will be determined upon the amount of electrons in that nucleus and how they spin in the direction in which they spin. Speaking more on electromagnetism, electricity is a characteristic of charged particles on an atomic level. These particles on the atomic level are electrons and protons. The small particles called atoms, they make up everything that exists. Magnetism is an attractive or repulsive force. The distance the force is effective at is called a magnetic field. So, magnetism is caused by moving electrons to positive charged protons. This current flow can have other electrons moving in an opposite way, which will negate the direction of the magnetic flux or assist and add to that magnetic flux if they were going in the same direction. So, to kind of summarize, the relation between electricity and magnetism is that electrical current flow in some direction causes a force called electromagnetic force by producing a magnetic field. The magnetic field is produced or exists through magnetic material. The presence of the electrical current flow in the vicinity of that magnetic material causes a force perpendicular to the magnetic flux vectorial direction, meaning that if anything is vectorial, then it has direction, the electromagnetic force, or EMF, will be perpendicular to the magnetic flux, contingent on the electrical current flow through some conductor. And that force, the EMF force, will be determined by how fast or how many turns on that conductor that the electrons or the electrical current flow happens to take. The importance of electric current flow and magnetic force. In 1820, a man named Hans Christian Ørsted used a battery to affect the way a compass needle pointed. A battery having current flow, electrical current flow, should I say, down some conductor, changed the way a compass needle pointed. Now, a reminder or disclaimer that a compass is comprised of some magnetic needle and the north part of the magnet in this compass. So no matter which way that I turn the north part of the compass, that needle will want to point towards that direction. And this will give the indicator of the direction in which we're traveling. So if I were to take, like Hans Christian Ørsted, a battery with an electrical current flow and place it near this compass needle, and I was able to manipulate what this compass needle determined to be north, or magnetic north, because magnetic north and true north are two different things depending on the deviation in which part of the world that you reside or that you're in taking the reading. But if I was able to change that compass needle and the way it pointed, and therefore I'm changing the magnetic field. So that concluded or established the relation between the two forces. So electricity and magnetism are used in almost every aspect of modern living. Electricity is ran through wiring around coils that cause a magnetic field that induce voltage onto another winding. The use of electrical and magnetic devices in modern living is so common that without them, most of present-day society would be lost doing the simplest tasks. People take for granted the luxuries that are developed for society by means of electrical current and a magnetic field. For instance, transportation on some trains use magnetic levitation to suspend a cart. We use electrical magnetic devices in data writing on hard drives and information transfer or sharing and communications and smaller electronic devices. And I think one of the biggest ones that we use, considering electrical and magnetic devices, would be the transformers sitting outside of your house on the power line. Because power company or your utilities company or what have you, a power plant, when they produce when they produce voltage and they put it on those power lines to send all over the city or all over the town, if you will, that power is so high, the voltage doesn't have to change. The power and voltage are two different things. That's two different topics. But the voltage sits on a power really high power at a really high value. That magnitude is very high. Now, the reason that they do that is because there's such thing as line loss. So when the path is open, or the path is closed, should I say, when the path is closed and there's no obstacles, no resistance in between it, there happens to be an intangible, if you will, an intangible type of resistance that negates some of that power. Or as in DC power, when something heats up, like in a resistor, that heat can be converted into dissipation of that power. So when the power plant creates this voltage that they send out through the power lines, that power is so high. What this does is it mitigates, or let's just say it negates, the power loss or line loss on that voltage, because if they're producing 120 volts RMS, which is AC, alternating current, down a power line, when I get it out my wall outlet at 60 hertz 120, that's what I'm looking for. But if I get it out the wall outlet at 60 hertz 100 RMS, volts RMS, some of my devices might not work all that well, because some devices use circuitry that is looking for quite possibly a knee voltage on a diode to allow current to travel through a path. Well, if I'm already stepping down power because it's considering that it runs on 120 and I'm stepping it down, well, now that I stepped it down, the power now it's not going to work in my device, and it's not going to see that knee voltage to turn that diode on. Therefore, it's inoperable and obsolete. So, in order to negate that power line loss, what power companies do is that they pump out high power and then step down in the transformer. Magnetic forces are used in technology for transportation, as mentioned in a previous slide. Like in magnetic levitating train, the current running through the coils cause change in magnetic force in the direction in which those force push. The maglev train is a means of transportation used by people every day that probably never consider the physical aspects behind the operation of the ride. The cart is levitated in the air and steers on its own due to the force generated by the magnetic field and current. These trains have no engines like common railroad trains. Instead, the force that is generated from the movement of the electrical current along some conductors create the force, the magnetic field, that pushes and pulls the magnetic material in some direction. Changing the field. Lorentz force law, stating a vectoral force is equal to a vectoral current flow times the length of some conductor times the magnetic flux. The force given can be mathematically expressed. A vectoral force will be attained with a combination of electrical current flow and a magnetic field along some conductor. This can be useful when working with precision on moving ahead for a hard drive disk reader to be able to manipulate the binary coding on the disk in order to store information properly. And the more precise that we can make this material, or the more precise that we can make the magnetic field, the more accurate and more information that we will be able to store. Changing the current. Increasing the electrical current in very small increments make it possible to precisely gauge and manipulate the magnetic force. Example given on a hard drive head on a disk reader or writer. Without the precise manipulation of the head, it would not be possible for the small increments to be attained on the disk platter. Faraday's theory. By Faraday's theory of EMF, changing the magnetic flux or moving the magnetic field in respect to change of time will cause current or some force called electromagnetic force. An important theory because it explains how electrical current can be attained by movement of magnets or magnetic material. This has been my presentation on electrical and magnetic uses. I hope that it was helpful, and I hope that you enjoyed it. Again, thank you. My name is Ryan Thomas, and this will conclude my PowerPoint.